Okay, so we are continuing with waveguiding structure in dielectric. So in this case, what we are expecting, that transmission loss is small compared to the printed lines. However, we have problem when we have bends. Now the mode designations, two different scenario we have, just like the surface wave. It can support TM like mode and TE like mode. So when we are saying TM or TE, you remember we are using some simplified model. In practice, we have all the 6 components of field, but here we are only considering the dominant field components. So in first case, sometimes it calls EMN Y, MN it represents the number of extremas along X and Y. So it is also called TM to Y. Y, you see, it is the perpendicular direction, wave propagating in Z direction. So in this case, we have EY component, EZ component of electric fields, and the dominant component of magnetic field is HX. So EY and EZ, EY it is perpendicular to ground plane, and EZ it is in direction of propagation. Do you remember the surface wave TM case? Similar thing. In TM mode surface wave generation, we also have normal component of electric field and also in the propagation of direction. So similar to that, here also the dominant components are EY and EZ. And in the second case, which we call TE to Y, transverse electric with respect to Y, we have EX component. So just like the TE case of surface wave, and HY and HZ components. So they dominates over other field components. So we are simply neglecting other 3 components. And M and N, it refers to the number of extrema of the dominant transverse field in the dielectric region with respect to X and Y direction respectively. So the lowest mode we will call TM11 or E11Y for TM mode and E11X for the TE mode. So let us see how the wave is confined inside the dielectric. We are showing the cross sectional view of one image kite which is sitting over this ground plane shown by this orange line, and we are considering 2 different scenario. For both of these 2 cases, A dimension is equal to B dimension. You say twice A, this is the width of this dielectric channel, B is the thickness of this dielectric channel. Now this is the normalized dimension K naught into A, when this is equal to 2.5. So most of the energy it is confined inside the dielectric. It shows the constant power contour. So 0.05 power contour, it is almost outside in air. Now if I keep on increasing the operating frequency, let us say we are considering a frequency just double of the first one in the same dielectric channel, you can say in this case almost 99% of my power is concentrated inside the dielectric channel. We have less fringing field in air, and this fringing field, just like the surface wave, it decays exponentially inside air from the dielectric surface. So when we are going to design any dielectric channel, we have to be careful about the operating frequency, and we have to carefully choose its dimension with respect to the guided wavelength lambda g, so that at least 99% of my energy is confined within the image kite or this dielectric channel. Otherwise, we will be facing crosstalk effect between 2 side by side lines. Here is a plot. It shows how beta by k naught it varies with frequency. So this B, it is a frequency parameter. It is defined as 4 by lambda naught into square root of epsilon r minus 1. So for this particular plot, we are considering epsilon r equal to 12 and a by b equal to 1. So that means width in this figure, width is double of the thickness, and you see the first mode that appears here, it is EY11. So it shows the importance of beta by k naught plot. So from this we can see what is the cutoff frequency of this mode. The second mode that appears for this given image kite is EX11, and you see the second higher order modes for TM, it is EY21. So for monomode bandwidth, so for not only for millimeter wave, for any RF applications, we always want to excite any guiding structure only in one mode. For example, for a rectangular waveguide, we want to use only TE10 mode. So if we have multiple mode excited inside the guide, so we face two problems. One problem, power is lost to higher order modes. We can't utilize those powers. So for example, let's say we are designing one SMA to rectangular waveguide transition or coaxial cable to rectangular waveguide transition. So in that case, we can design it with respect to only one mode, let's say TE10 mode. Now if somehow TE20 mode is excited inside your rectangular waveguide structure, that power will not be collected by the coaxial cable. So it's a wastage for my circuit. At millimeter wave frequencies, already there are many sources of losses, and loss increases with frequency. So we can't tolerate any other loss. This is the first reason. And second reason, that different modes have different velocities. So that means we will be facing dispersive effect. So pulse, it results pulse dispersion. So that's why this single mode operation, or we call it monomode bandwidth, that is very important. So for standard WR90 rectangular waveguide, we know the cutoff frequency is approximately 6.3 gigahertz, and we use it over 8 to 12 gigahertz, and it is the monomode bandwidth of that WR90 waveguide. Now for the image guide, if I look at these values, so obviously if I plot alpha, it will be infinite almost at the cutoff frequency. So we have to take away from it, and the monomode bandwidth, if you compare the value with rectangular waveguide, it is much smaller. So this is another problem with image guide. And not only that, this line near to cutoff frequency and at higher frequencies, it becomes dispersive. Always beta by k naught is more than 1. So it's supporting only slow wave. We face two problems for image guide. One is lower monomode bandwidth, and another one is dispersive effect. So how then, looking at these 2 point, how we can choose the dimension? We have some design graphs for that. So here it's showing A by B versus bandwidth plot considering dispersion effect. We are considering that dispersion effect is minimum within, let's say, plus minus 10%. So in that case, this is plotted for a given image guide with fc equal to 14.53 gigahertz. So we see that if I change epsilon r values, then the dispersion bandwidth, it changes. Smaller epsilon r, it has higher dispersion bandwidth, and not only that, it is highest for A equal to B. So then the first design rule for image guide, you take A is equal to B, or width should be twice of that of thickness, and from this, if we want to minimize dispersion, we have to choose a lower epsilon r. Now look at the right hand side. We are considering here guiding bandwidth or monomode bandwidth, so that no higher order mode is present here. Here we have opposite variation. At A equal to B, it is having highest value, but with increasing epsilon r, now the bandwidth is increasing. So, from this design chart, design graphs, we have to choose an optimum value depending on our requirements. We are giving preference to less dispersion or maximum guiding bandwidth. Next is insular image guide. So, what is the need of insular image guide? Insular image guide, actually it can decrease the conductor loss further compared to image guide. If I go back to image guide, you see this is the basic image guide structure. Now, we have perpendicular electric field component and parallel electric field components. So, EY, it is maximum on the ground plane. So, it is associated, it will induce current and associated with high conductor loss. Here also, if I look at the constant power contour, maximum power is confined near to conductor, which will give me high conductor loss. We are designing image guide for lower loss compared to printed lines. Then again we are facing with high loss. So, how we can avoid it? Now, we have some very good dielectric material for which loss tangent value is very small. So, if we can avoid conductor loss to some extent, we can actually decrease the overall loss. So, how we can do it? Intentionally, we are introducing one more layer of substrate of dielectric constant epsilon r1 in between the dielectric channel and the ground plane. Epsilon r1, it should be much smaller compared to epsilon r2. So, now we are again plotting the constant power contour. So, if I increase the frequency, you see, to k naught a equal to 5, here since epsilon r2 is much higher compared to epsilon r1, so most of my electromagnetic energy, it will be confined to this top layer inside the channel, and that is how the maximum point we can shift it from the conductor, right. So, we will be facing only the dielectric loss and we can minimize conductor loss. So, that is how insular image guide provide lower loss compared to image guide. So, we have one additional parameter here, the thickness of the second dielectric and the dielectric constant of the second dielectric. So, one observation we have that epsilon r1 for this bottom dielectric, it should be as small as possible, so that most of my electromagnetic wave is confined to this top dielectric channel. Here is the beta by k naught plot versus normalized frequency parameter B. We are, for this example, we are considering A by B equal to 0.5. You look at the dimension, how we define twice A is the width and B is the thickness of the dielectric channel. So, that means thickness is equal to width, and epsilon r for the lower material, it is 2.25, for the channel it is 9.8. In that case, again the first mode that appears is TM mode, TM2Y, EY11, and second mode is EX11. But if I look at the characteristics of this plot, you see these are for different values of d by b, it is more straight. We can say it is less dispersive compared to the image guide. And we are increasing, if I decrease d by b from 0.2 to 0.05, what will happen? You see the cutoff frequency, it decreases, and monomode bandwidth, it increases, but at the same time we see the line, it becomes dispersive. So, the actual solution, it will be an optimum one in between these two extreme values, and the suggested value of d by b is 0.015 to 0.15. So, let us see the loss plot, because loss is very important at millimeter wave frequencies. We are plotting alpha d and alpha c separately in dB per meter, and we are considering again a by b equal to 0.5, epsilon r1 to 0.25 and epsilon r2 9.8. So, alpha d it increases with frequency and alpha c it decreases with frequency. Why? Let us go back to the power contour plot. So, at low frequency you see some of the power is near to conductor, we are expecting higher conductor loss, but as I increase frequency almost all of this electromagnetic wave propagation is through dielectric channel, this top one. So, conductor loss will decrease, but dielectric loss will increase. So, if we can choose a dielectric layer with minimum tan delta value, in that way we can decrease the overall loss. So, this top layer it represents d by b equal to 0, that is nothing but the image guide where we do not have any epsilon r1. So, you can compare the alpha c for these two cases. In the first case, when we have image guide d by b equal to 0, alpha c more or less it remains constant with frequency, but in the second case it decreases significantly. So, that is how we can decrease overall loss for insular image guide. But this type of waveguide has one more problem. Whenever we have bend, it is associated with higher order modes and we have leakage from these modes. So, that is why we have again one more design graphs. It suggests how to keep your leakage loss minimum. So, it is leakage due to radiation mainly alpha r, dB per radian angle we are plotting. So, we have some radius of curvature, it is given by capital R, and we are considering it for different r by twice a value. You remember a is the width of the channel. Now, for r by 2a equal to 2, this is the graph, and if r by 2a equal to 20 when r is small, so this is the graph. So, from this then you have some idea how to minimize the leakage loss from insular image guide. Next one is trapped image guide. So, what is the difference with the previous one? We are using a metal packaging somewhat looking like a rectangular waveguide. Inside we are placing the image guide. So, this is called the trapped image guide. So, the packaging wall separation from this waveguiding structure, it should be sufficiently high so that it does not disturb the image guide mode. What is the advantage of that? We can avoid crosstalk between two side by side lines, and another advantage is that we can avoid that radiation loss. So, how? If there is any bend, let us say there is some higher order mode excitation and from that we have radiation, but since now it is an enclosed structure, so all of this radiation will be reflected back from this boundary wall and it will again excite the original mode inside the guiding structure. So, that is how we can minimize leakage loss as well as crosstalk. So, not only for image guide, similar trapped guide we can also design for insular image guide. Next one, non-radiative dielectric guide or inertia guide. It is another popular form of guiding structure at millimeter wave frequencies. So, here we will see that mostly energy propagation it is through the dielectric layer. So, that is how we can minimize conductor loss. Here if you look at the structure, we are using a dielectric slab in between two metal plates. You look at the structure. So, we have one dielectric slab of thickness B and it is placed in between two metallic ground planes. Wave propagation, it's in z direction, and the metallic ground planes, it's in y z direction. Just like surface waves, we have again TM mode and TE mode. So again we are having air dielectric boundary, we have hybrid modes, but we will be using simplified model considering only the dominant field components, and we have three dominant field components just like the image guide and insular image guide. So we can define in similar way the mode names, but we have one more popular name. So better let us use those popular names instead of just TMY or TE2Y. Those popular names are LSM11 for the fundamental mode and LSE11. The full form is longitudinal section magnetic. So that means in the propagation direction mainly we will be having magnetic field component, and in the second case longitudinal section electric. So in the propagation direction mainly we will be having the electric field components, and we will see for high epsilon r the cutoff frequency of LSE11, which is actually TEY, is lower than that of LSM11 mode. Let us look at the field configuration. It is showing the three-dimensional field plot. So we have a dielectric slab in between two metal planes. So magnetic fields mainly this is in ZX plane, right. In the direction of propagation we have magnetic field component as well as in perpendicular direction. And if you look at the electric field components, here all the three electric field components are shown, but in the propagation direction Ez is minimum, we can simply neglect Ez. So then the dominant electric field components will be Ey and Ex component, and they are perpendicular to propagation direction. So that is why we call it longitudinal section magnetic. In the direction of propagation we have negligible Ez. So mainly it is magnetic. In the second case we have another scenario, it is called longitudinal section electric. So we have dominant electric field components as Ez and Ex, and for magnetic field it is parallel to YZ plane, and again in the direction of propagation Hz component is negligibly small. So that is why it is called longitudinal section electric or LSE mode. Now just looking at this field plot, can you say which one is lossy? So if I compare left hand side and right hand side plot, inside dielectric you see the electric field components Ex having higher values, which is perpendicular to this conductor, and for this left side this electric field component having highest value, it is actually in between these two plates which is parallel. So right side we are expecting higher conductor loss since its electric field maxima is near the conductor plane. That is why LSE mode it will give you higher loss compared to LSM mode, and not only that, these two modes are orthogonal to each other. So that means if I excite this structure in LSE configuration, LSM mode will not be easily excited or vice versa. Next is the mode separation. We are plotting the cutoff frequencies versus B by A. So LSM11 by LSE11 versus B by A into root epsilon r minus 1. So LSM11 is having higher value than LSE11. So that means the cutoff frequency of a longitudinal section electric is smaller compared to LSM, and we are plotting it for different values of epsilon r. If we increase epsilon r, we see the mode separation or separation between these two cutoff frequencies increases. So, it is a function of epsilon r. Not only that, it is also a function of b by a. We have some optimum b by a for which this mode separation is highest. So, if we want to excite this structure only in that, we have to choose the dimension b, a and epsilon r accordingly. So, but in practice people prefer LSM mode. Why? It has lower loss compared to LSE mode. This is the plot of beta versus frequency. So, for a given structure, we are plotting beta. For LSE mode, as expected, it is having the lowest cutoff frequency, beta equal to 0 approximately at 76 gigahertz for this typical example. Next mode that appears here, this is LSM11. Look at here the mode designation. Next Harada modes, the pink one, LSM21. So, if I use this channel for LSE mode, then the effective bandwidth I can utilize from 76 gigahertz to approximately 85 gigahertz. It is very this narrow band, but usually people prefer LSM mode due to lower loss, and if I utilize it for LSM mode excitation, it is from 85 to almost 100 gigahertz. So, for monomode bandwidth for LSM will be higher, and for LSM we are not expecting any LSE mode generation. Why? I said that they are orthogonal to each other. Okay, let me explain the orthogonality a little more in details. Again, we will be considering rectangular waveguide, the very basic structure. We have a rectangular waveguide and it is supporting TE10 electric field configuration. If I plot the electric field, we are having maximum on the central plane and then it decreases left hand side and right hand side. Now, if I keep on increasing the operating frequency, it is highly possible that this side also we can excite one more mode. Let us designate it by TE01 mode. In that case, we will be having maximum on the central plane here, and then on the side walls it will be 0. These two modes TE10 and TE01, they will be called orthogonal to each other, and if we do not use any bend or any other structure, there won't be any mode coupling. That means this rectangular waveguide, or better let us take a square waveguide, so that the cutoff frequencies for both TE10 and TE01 mode is same. Then we have TE10 in this direction and TE01 in this direction, and the square waveguide, it can support these two wave propagation at the same time without any interference between these two. They are called orthogonal to each other. So, by using this orthogonal property, simply we can double the bandwidth. Similar thing is possible for NRT guide also. If I excite it in LSM mode field configuration, in that case it will not excite longitudinal section electric mode, but remember, only if the structure is straight, the guiding structure is straight. If I use any bend, it can generate higher order modes, and from that higher order modes LSE mode can be excited. So, we have to use some mode suppressor. So, there are some components which can suppress that unwanted LSE mode if excited from that bend. Let us compare the losses. For the left hand side, we are using a dielectric slab of epsilon r 2.56 and a plate separation is 5 millimeter. We are plotting total loss and dielectric loss for both longitudinal section magnetic mode and longitudinal section electric mode. As we expect to see, for LSM mode, total loss is lower than that of LSE mode because of that conductor loss. Conductor loss is lower for longitudinal section magnetic. Now, right hand side plot loss in dB per meter versus A plate separation. So, if we increase plate separation, loss decreases for both longitudinal section magnetic and longitudinal section electric. Here are some more plots. In this case, what we are doing, we are plotting loss in dB per meter versus frequency for 3 different types of substrate parameters. We are using 3 different dielectric constants for that. Teflon dielectric constant 2.04 and tan delta 0.0015. We are considering plate separation 2.7 millimeter and the thickness of dielectric 3.5 millimeter. In the second example, polystyrene epsilon r 2.56, A and B values are 2.7 and 2.4. Third example, alumina, now epsilon r is much higher, 9.5, A same value, B 0.93, this is to minimize loss. Now, we are plotting the total loss and the dielectric loss. If I concentrate on any one plot, polystyrene, let us say, polystyrene it has 0.0009. So, mostly the loss is due to dielectric, right. We are doing it for LSM, conductor loss is minimum. So, the difference between this total loss and dielectric loss, that is due to the conductor. At cutoff, it is going to infinity, and if I move away from cutoff, it decreases. Variation is somewhat looking like rectangular waveguide. Now, consider alumina. It has lower cutoff frequency since A is same, but epsilon r is higher. So, it is having the lowest cutoff frequency among these 3, and for this one you see again we are having similar plot. Now, if I compare these two, red curve and this black one, so almost similar epsilon r, but for this black one it is showing higher loss. Why? Because of its tan delta. For this black one it is 0.0009, whereas for Teflon it is 0.0015. So, mainly for LSM mode, what we see? Main source of loss is dielectric loss. We can avoid conductor loss to some extent. We have to choose a proper dielectric material which will give you small loss tangent value, and you can design a waveguiding structure whose loss is very close to air field rectangular waveguide, and that is how we can actually obtain at very lower loss. But the problem again we face at millimeter wave frequencies is fabrication problem and loss from any bend if you have in your MMIC. Some other guides, group inertia guide. So, in this example you see the middle part we are using a little thicker, and this it actually increases the separation between two different modes. This is another example, H-kite and group kite. So, there are different types of waveguiding structures. Those came in 1980s and some of them in 1970s. When they came, it was thought that they will replace all other waveguiding structures because they provide much lower loss. But for most of these structures, the common problem we face is excitation of higher order modes. Whenever we are going to design any components, we have to deal with bend, we have to deal with crossing or junctions, so we can't avoid them. And whenever we have a junction, we will be having higher order mode excitation. Here are some example. This is H-kite. It looks similar to NRT, but the plate separation A in air, it is more than lambda naught by 2. For NRT, A in air, it is less than lambda naught by 2. So, basically we are increasing the cross sectional volume, that is how we are decreasing loss. This is for the H-kite. We have one more version of this. So, we are simply replacing the dielectric by air, and that is why we are increasing the thickness of this middle part. So, the operation or mode characteristics almost similar for both of these two cases. We can have lower loss, even lower than air filled rectangular waveguide, but they are not being used currently because of fabrication problem and because of higher order modes. So, these all from different types of dielectric guides. Next, we will discuss about how to excite these guiding structures, because at the end of the day we have to measure the structures whatever we design, and already we discussed the measurement instruments, they come with coaxial cables. So, we need some adapters or some excitation schemes that so that you can measure your structure, which may be designed in NRD, SIW or microstrip line, but you have to measure it by coaxial cables. Okay, thank you.